This giant corrugated steel tube lying on a riverbed in the north of England is the basis for a remarkable method of bridge building. Remarkable because it's inexpensive, simple and quick, and produces an arch so attractive it would make the Romans proud. This film will follow the construction of a composite earth steel bridge designed by Tubo Sida Italiana at Bishop Auckland. The contract was to carry a bypass over the River Gauntlet, a job that turned out to be the largest corrugated steel culvert in Europe at the time. Cost and an aesthetically pleasing landscaped embankment were the two main factors why Tubo Sida won this contract. But the work was carried out by Durham County Council's own direct labour force. Tubo Sida supplied the steel plate and an engineer to supervise the erection. And after that, the composite earth steel structure was so simple it could be built with a small, unskilled labour force. Let's follow that construction now. In fact, simplicity starts with nuts and bolts. The individual corrugated plates are just bolted together. They're easily handled and can either be assembled onto the prepared bed or pre-assembled into panels and bolted together, which is happening here at Bishop Auckland. Handling is easy because the plates are only 1 metre wide, with the circumference varying to a maximum of 2.5 metres. And of course they're easily stacked because of the corrugation, so it's neat as well as simple, with little space on site being taken up by building materials. Because it's such a straightforward construction job, difficult ground or weather conditions do not affect progress. As the snow settles on the Durham landscape, the job speeds on. Once the plates are bolted to the required length, the panels are prepared for the crane to take over the heavy work, lifting them into position on the valley bottom. As the panels are lowered onto the riverbed, another crucial construction factor becomes obvious: the lack of any complicated foundation work. There's no need for piling with this design. The only foundation necessary is an easily prepared granular bed, 1/2 metre in depth, to support the multi-plate structure. As you'll see in a few minutes, this giant corrugated tube will soon disappear from sight under many tons of earth and landfill, forming the inner shell of the Gauntlet Valley embankment. The corrugated steel will be compressed under the load of a compacted backfill, giving the arch its natural strength. An embankment was favoured by the local highways authority because of cost and appearance, a far better blend with surrounding landscape than the alternative, an expensive and unsightly viaduct. Of course, economics are an essential part of any construction project and often determine the viability of a scheme. The savings produced by the use of a Tubo Sida earth steel structure over the cost of a rigid conventional structure are impressive, from 35 to 50%. That this type of structure is economical can be seen by following the process from the design stage to completion. A minimum of design time is required. Piling is unnecessary, formwork, steel fixing, stripping and curing are eliminated. Construction is fast, using a minimal amount of unskilled labour, and very little manufactured material is used other than the steel plate, the bulk of the material being locally dug fill. We're not only concerned with economy, but also with design strength. Of course, arches are famous for that. Indeed, some of the masterpieces of the Roman military engineers are still standing as tributes to their skills as bridge builders. And although this bridge at Bishop Auckland is only coping with a small river, it could just as well be a raging torrent. The structure could quite literally be a bridge over troubled waters. As for the technical specifications, the materials are manufactured in the EEC, and all comply with the requirements of the United Kingdom Department of Transport specifications for corrugated steel buried structures. The steel plate at Bishop Auckland is 7 millimetres thick and has an extra protective coat of 250 microns of mineral-filled thixotropic bitumen. And the size is certainly impressive, 75 metres along the bottom centre line, with a span of nearly 10 metres and a rise of just over 6.5. "145 tons of structural plate assembled in a period of not more than 6 weeks with a crew of 5. And flexibility certainly goes with ease of construction. There's no real limit on how long or short or how curved these bolted panels can be. During the construction, it's critical that the shape of the structure is maintained and that any movement is monitored. To make sure that these factors remain within their tolerance, strain gauges and plumb lines are fixed inside the structure and readings are taken and recorded by the engineer. So within the space of only a few weeks, the motorists of Durham get a good idea of how the Bishop Auckland bypass will cross the River Gaunless, and the structure's natural arc gives a hint how it will eventually blend with the surrounding countryside. With the steel structure intact, it's now time to begin the backfilling process that will compress the arch and give the whole structure real strength. The first of many lorry loads of locally dug fill material are brought to the site and worked into position around the giant tube. As we've said, earth steel structures work by deflecting under load to mobilize passive support in the surrounding fill. It follows, therefore, that the better the quality and the compaction of the backfill, the stronger the earth steel structure becomes. Each layer is rolled, compacting the fill to the degree required by the turboceder engineer. This process is repeated until gradually the steel is entombed in a solid earth structure. This man is driving a sample core into the compacted backfill. Compaction at the optimum moisture content to the specified dry density is critical. And to make sure that this is carried out, regular tests of the compacted material are made during the backfilling procedure. Modern electronics mean an instant readout is available on the quality of the work so far. Meanwhile, the shape of the steel tube is still being monitored carefully. Gradually, after layer upon layer of backfill, the shape of the final embankment starts to become clear. Now the engineers turn to the next stage of strengthening the structure. In the case of a large span like the one at Bishop Auckland, it's critical that the top arch movement is controlled. It's very difficult to compact satisfactorily against the top radius of the arch. So a concrete thrust beam is built along the entire length of the structure on each side at an angle of approximately 40 degrees from the vertical center line of the top radius. In other words, the 10 o'clock and 2 o'clock positions on a clock face. This camera angle effectively shows how the thrust beams provide the necessary vertical faces against which the backfilling can be compacted to the required density. By now, the gentle contours of the landscape culvert are increasingly pleasing to the eye, and the construction is ready for the final push, the backfilling operation that will compress against the top of the steel arch and blanket the whole structure ready for the new bypass to be laid. Meanwhile, the top edges of the culvert are being prepared for their finished appearance, the necessary structural work carried out to form the base for the finished cladding. This man is working on another vital finishing operation, a concrete collar for the edges of the culvert where the corrugated steel ends are left exposed. The concrete provides the necessary rigidity to finish off the contoured edges. And so the backfilling and landscaping operation moves into its final stage. From now on, it's simply a matter of earth moving until the culvert is ready to take the Bishop Auckland bypass. The fact that the bulk of the material used in this culvert design is locally dug landfill means that these structures are ideal in remote sites. There's no need to transport vast amounts of materials, so reducing the construction costs yet again. This could be particularly relevant in third world countries, where the need to preserve foreign currency is paramount. The maximum utilization of locally produced material with a low foreign currency element is assured. But of course, it also makes sense for any site. So the advantages of two-seeder design are seen in action at Bishop Auckland. Economical, with savings of 35 to 50% compared with rigid structures. Simple to construct and quick, using a small, unskilled local labour force with two-seeder supervision. The ability to construct in difficult ground and weather conditions with no need for piling. Entirely flexible to design need, and pleasing to the eye and to the environment. And so the bridge over the River Gormless nears completion and proves itself capable of taking weight, even if it is just construction traffic. The final cladding operation begins. The river finds its new home. The Durham landscape gets a few more gentle contours. All that's needed now is a little greenery. Earth steel structures are still a relatively new design concept. But of course the arch is one of the oldest of bridge designs. Today though, it has a bright new future, with a span rate that can be increased because of the strength of the composite earth and steel structure. And with the increasing acceptance of these cost-saving structures by engineers, and the realization that their span is not restricted, the aesthetically pleasing arch should once more find its place in modern bridge design.